Thank you for inviting me for this fascinating conference. I actually changed my lecture quite a bit based on what I heard here and the people. And it's going to be kind of an interactive lecture, at least the first half. So if you feel like participate. Before I start, I want to thank a few people that contributed to the work that I'm going to present here. First of all, several people from my team, various PhDs and postdocs, Benedetta Himmler from Italy, Shachar Mandelbaum, and Lior Reich, Roni Arbel from Israel. That's mainly the work I'm going to present. Two people, Elad, that is now in Harvard Medical School, and Sami, which is in Paris, and three Parisian colleagues, Stan Dihan, Laurent Cohen, and Joseph Saheb. I'm actually, so this is one thing I changed. I kind of traced back my first work, which is related to this talk, and I realized that several scientific papers and one philosophical debate actually directed me into my first study on the brain. And the question is actually quite, it's thought experiment that Molinet wrote in a letter to John Locke, and basically he asked a very simple question. Let's say I was born blind, and a lot of what I'm going to show you here is work with people that never had any visual experience. Either the retina didn't develop, or they didn't have any visual recollections from day one. Let's say through some miracle, for example, today you have such a kind of miracle. For example, Project Prakash, which is a project that is in India, an MIT vision scientist that decided, Indian origin, that decided to come back to India and treat curable blindness. There is a lot of curable blindness that is not treated, although it's a very simple operation, like a cataract removal, congenital cataract removal. And basically, let's say we are giving a sight to somebody that never saw, and of course he knows to differentiate a sphere from a rectangle by touch, of course. Will he be able, once he adjusted to his vision, to immediately recognize what is the sphere and what is the cube? Okay. Any guesses? What you think would be the? Will he be able to do it by his gained vision or not? No. No. Yeah. So we get some no's, we get some yes. We could have half hour on this or 2 hours. But actually now this is an experiment that was done in the last 2 years. But when I did my first PhD work, it was not possible to do this experiment. So we actually did a very simple experiment and asked whether what is the representation in the brain to deciphering shape from vision? What is the brain network that is involved in recognizing shapes by touch, and doing it both with sighted individuals and people that never saw in their life? And what was quite amazing is that we actually found a completely new brain region that was thought to be a visual system area, but it can develop without any visual experience. And it's actually deciphering, it's activating to both vision and touch, but not to audition. So we hypothesized that this is actually, we thought of it as a sensory area, but actually this is an area to perform some task or computation. And this is the computation of creating 3D exact shape. From audition, you get some sounds that are completely associative, but from vision and touch, you get actually shape. And actually, the brain have this operator, and we term this area LOTV for some reason. And actually, recently, we tested this hypothesis, and this will highlight some of the lecture here, by an algorithm that I'm going to train you on a little bit for 1 minute, to take visual images and render the shape information in sounds, just like bats and dolphins. And then scan the brain before they learn and after they learn. And we found out that only after they learn to extract shape, this area is getting into action. Okay, so this is some support, and actually, so this is basically in the heart of the half of my talk. So part of my talk will be dedicated to how our initial efforts to work with some technologies to have assistive technology to blind, like a cane, electric cane. We developed with work to up to 5 meters, or this type of technology using music to represent vision. can help us to understand the brain. I'm a neuroscientist, is what I do for my living, so I'm using it to understand the brain. Okay. The second part is actually connected more to this kind of selection you have today, which starts to emerge, and also to highlight this is usually an introductory slide I have. Maybe for this conference it's a bit trivial, but we are actually now in the middle of a big revolution. When we have almost, it was 500,000, now it's getting closer to 1 million people that are having this brain electrical stimulation inside the brain that interacting with the brain, which is can be some kind of a definition for a cyborg. Some of them are built on a very deep understanding of a brain network. I will give, actually I added something that I didn't plan to talk about, but that only the understanding of the brain mechanism help us to develop a technology that is helpful. So this is, for example, cochlear implants, and this deep brain stimulation are quite successful, or very successful in terms of restoring hearing and some relief to Parkinson patients that don't respond to medication. But we have also a lot of other types of chips that are interfacing with the brain. Just to give you a couple of examples, one is chip to restore vision, which is very partially successful if you want to be very supportive of what it's amazing. It's actually working 100% to retrieve vision experience to somebody that is late blind. But form vision is a very complex thing here, and actually we will discuss it in a second, but today there is between tens to hundreds of pixels of electrodes, and you achieve only after 1 year of very extensive training, very, very limited capabilities, and that are not actually met by what was supposed to be using this level of resolution. And again, in some other cases, I will just give the example, for example, of the deep brain stimulation. A deep understanding of the brain mechanisms can allow us to retrieve vision. I do want to highlight to one work that you presented, Nicolelli's lab, and this is another direction which all this brain machine or brain implant interface is going. It's a beautiful experiment, and I would show some human similarities by non-invasive and even invasive mechanism to try to create new senses that we don't have in our spectrum in the brain. So in this case, Nicolelli's lab implanted the electrode in the body representation of the mouse, one of the famous homunculus. And you know, one question is, for example, how these two entities, we know that we have one entity for the brain in the primary somatosensory cortex. How would these 2 or 3 entities that you are experiencing will be translated in the brain? Just something that I thought would be fascinating after hearing you. But in this case, he put the electrode in the body area of the brain, but connected it to a camera that gives information about night vision that the mouse doesn't have. And the mouse was able to integrate this electric stimulation that have a meaning that comes from a camera with his own brain activity to respond to it. We don't know what he's experiencing. With human, we can start asking, and I will show you some of this. But this is another direction which all these brain-machine interfaces. So you can think, for example, about a situation in which a successful cochlear implant maybe can give you, in addition to stimulate the nerves, some additional information or some other implants in the brain. So this is something that's also happening here, and it's really already in the borderline of all the ethical issues that were discussed here. Yeah? And there is a lot of gray zones. Some people are doing it to themselves, so can you prevent them or not, and so on and so forth. I will also talk a lot about non-invasive approaches, just like Ido presented, and it will sometimes show how the companies go very strongly in these directions. In some cases, it's amazing, like I will show you here. In some, there is non-invasive solutions that are not being promoted enough from various reasons. And it's interesting to see, you know, how you compare the biological or invasive options of restoring versus the more non-invasive parts. So this is also something that will go on and going on a lot. So just 1 minute of this example. Parkinson's disease is caused, again, we can have 2 hours on this, but I will try to summarize it in 1 minute. Is caused by a dying of the of dopaminergic neurons in the S and C nucleus, in the basal ganglia, and a deep structure in the brain. And this cause, actually the tremor that we are seeing is just a little of a side effect. The real problem is a frozen person, so it's very difficult to initiate movement. The tremor is just a little side effect, okay, comparative to this problem of freezing or starting a new program. Okay, and the reason is that there is increased inhibition because of this dying of these neurons in the basal ganglia. So following understanding tens of years of research of understanding all the circuits, the people that came up with this idea of deep brain stimulation, first by doing a lesion, later by implanting electrode that imitate lesion, actually suggested, again I'm not going to say why here because we don't have time, that if you are inhibiting the information from a different structure that is causing inhibition, then you are actually canceling the inhibition. And I'm just going to show you a movie. So basically you implant here electrode, so you have damage here, you add damage here that is reversible, and you cure this freezing, which is the biggest problem in Parkinson. So just this discussion that whether brain can help us to do technology, if we have good understanding of the system, yes. If not, sometimes it's the opposite. The implants can help us, or the interaction of technology with the brain can help us to understand it better. This is what I will try to show you here. So in this case, you see here, let's see how is my luck with movies. This is actually something I downloaded from YouTube, so I won't have issues with... And this is a Brazilian guy that just has an implant, a deep brain stimulation implant. And he has the battery for the implant. At the moment, this is the technology here. You can see it on the body. And actually, you have this control device that he can disconnect it. Okay, it's in Portuguese, so unless you're Brazilian, you understand it. You see, quite a normal guy.
Senhores, aqui temos um magnético que liga e desliga o DBS. Start. Para baixo. Caralho, senta. Liga tudo. Aqui de novo? Liga, não quero. Não, hoje a gente estava vendo só ter vídeo de baixo. Tem que sentar.
Okay, now he's going to disconnect the stimulation into this other structure that is not damaged, that has these electrodes inside it, this chip. And you see the tremor, but also the difficult to produce movements and so on and so forth. And then he will reactivate it and he's again acting normal. And this is there is already tens of thousands of examples like this, and it's quite successful. So one issue that is I can open to discussion here is that now it's to which direction is it going? Because now there is a lot of clinical trials in other directions. So for example, there is clinical trials on mental illness, and then maybe the next step will be getting to people that are not depressed, just some chip to get high. I'm just speculating about it, but it's something that we need to consider. Clinical trials for obesity, yeah. So and people losing appetite using this. How about where is the border of here? Where is the selection? And the last was what I mentioned about Nicole's lab, using this type of interfacing directly with the brain to create new senses.
My name is Neil Harbison at the age of 11.
Here I want to show you actually a movie about someone that did it initially non-invasively and then invasively. Is a colorblind person that actually took a camera, averaged everything that is in the camera into an average color, and represented it with one pixel that just telling the average color of what we is doing by the sound, by the frequency of the sound. So if it's a high frequency, so he's stretching the spectrum of vision into this. So this is Neil Harbison.
My name is Neil Harbison. At the age of 11, I was told that I couldn't see color. For the last 10 years, I've had this antenna attached to my head that allows me to hear the frequencies of color. So it's a direct transposition of light into sound. It's like a new sense.
ניל הבריטי התגבר על לקות הראייה שלו בטכניקה דומה. הוא השתיל בראשו מצלמה שמתרגמת את תדרי הצבעים לתדרים של קול. מבחינתו, הוא כבר רואה צבעים. יכול לספר לי?
כן, ובעצם במקרה הזה הוא פשוט... In this case he basically went on and do himself the operation and the movies?
כן, לא, רק להחליש קצת עבוד.
אין בעיה.
תודה.
Yeah. So in this case, we have somebody that is trying to create on himself something that is not there. So I want to describe to you a project that we did on blind with blind individuals, and basically there is, as I said, there is this bionic eye option, but we need to explain why there is so much variability between people and why it's so partially working in a situation that some patients don't even manage to read one word or two letters after 1 year of rehab. Yeah? Of course, you would see from the brochures of the company a different picture, but working with this patient, I can tell you this is the situation, okay? You see the best example, or the best 5 examples, but in this case, as I said, the miracle of restoring the sensation of vision, even if you didn't see for 30 years, is instant. So you stimulate the electrode in the retina, in this case of the phosphines, you get, and for some people, this is the world to them. Okay, so as like Ido said, it's a very personal thing. Some would say restoring something like as I can know now if there is a light or no is wonderful. But for another, he would say, you know, if I cannot walk on the sidewalk, or if I cannot read one letter, it take me 30, 40 seconds, and then I need to, then it's not enough. Okay, so. In the next 5 minutes, I will try to give you one of the... So part of it is that we cover only very small part with bionic eyes of the retina. But there is, I think, some other, and I won't show you the movie due to time, but I want to stress one point. And this point was actually missing from this project for a long time, and we have an ERC project to introduce it into it. And this was that we... think about vision, or an engineering point of view of vision, is saying is we have some input in the outer world. It can be this face or this letter. We have image on the retina. This is encoded in neurons that travels into the visual cortex, and this is how we see. So if we just restore this part to a brain that didn't see for 20 years, 30 years, 5 years, then it's going to, if we get enough resolution. So in principle, with 60 electrodes, or even less, you are supposed to see this E immediately. Not to take you 1 year, and some people cannot do it. So something is not full in this image, in this picture. Just to give you 1 or 2 quick examples to explain why this is not the whole story, I want to mention that first of all, we have the electromagnetic spectrum. Vision is taking only this very small part, and all the bionic eye project try to only give at the moment grayscale information in this range. But what the people like Nicolelis or some projects in our lab try to do is to introduce also some other parts of the spectrum into the information. But in our case, non-invasively. But as I said, the field is going in the direction that people are going to do it, or starting to do it also invasively, to try to bypass some of the cognitive aspects that I'm going to mention in a second. So just 2 very quick examples. I really like this example because it's something that happened to me spontaneously, that I used a lot FedEx, and one day after 100 times that I looked into it, suddenly I saw something that was not there. But in my retina, nothing changed, yeah? So how many of you know this logo, but now for the first time, see that between the E and the X there is an arrow? Raise your hands. Who see the arrow for the first time? So almost all the audience. So what happened here? The input of the retina didn't change, but 1 sentence or 2 sentences that I sent will change your vision forever. I promise you, if you go back to Netherlands or to the US and you see a FedEx truck, the arrow will jump on you. You cannot ignore it anymore. And maybe also you remember this weird guy that came in purple and gave this talk. Orange. Actually, I have some collaborators in Amsterdam, so I'm a big supporter of your soccer team. Anyway, a second example that stormed the internet several like 2 years ago, let's do a little experiment here. How many of people see this dress like me in the right colors, which are white and gold? Who see this as white and gold? Raise your hands. I see here a few normal people. Actually, we are wrong, but we'll get into it in a second. While the other, I guess, see it in blue and black. Now, just to remind you. Yeah, so what's going on here? The input is to all of you the same image, right? How can something basic, now I want to remind you the physics. We think about color as 400 to 700 nanometer. Blue is one part of the spectrum. Gold is another part of the spectrum. Now black and white. Black and white is the opposite. There is light, there is no light. Okay, so the bottom line here, and I can explain to you part of this. Actually, it's what happens in the brain is that your brain interprets the same signals in a different way. So people that are, I can demonstrate it with this line. You can see here a gray line. If the background is black, then you see here it more white, and if the background is bright, then you see it more black. Okay, so basically, your brain interpreted the reality based on the context. And the people that see the dress like me, yeah, the smart people that are wrong, you can be smart and wrong. Anyway, so what do they think is they think that the dress is being, no, sorry, this is the, yeah, this is the people that see it white and gold, yeah? So if you think the dress is being washed out with very bright light, your brain may perceive the breast. Sorry, let's start. Yeah. It's very confusing. Okay, so basically it's an interpretation issue. The people that see it white and gold think that the dress is in the shadow relative to the background. So the brain says, okay, I need to remove the darkish color, the blue cast and the dark cast, and I perceive it as white and gold, and a few. The other people think that the dress is actually being washed by a very bright light. So the brain removes the very bright colors, and you are left out with blue and black. Okay? So this is another, so the bottom line of all this, I can show you many of this, is that we actually see, physically see colors, shapes, and grayscale. I showed you all these examples, in some cases, with the brain, not just with the eyes. So this is actually, I would skip this. Actually, there is a even more interesting phenomenon. This is a hidden advertising to my brother, Amir Amedi, which is the head chef of the Palomar in London. And this is a little thought experiment to those of you that are familiar or not. I think for this crowd, I think maybe it's the most strong demonstration of this point, is that if you put one image on your right eye, let's say Tomer, and you put his beautiful polenta on the left eye, the question is, what will your brain see? And we can spend the next 7 minutes, sometimes when I have more time, we do some debate on this. And there is a lot of answers, but actually almost no one guesses, if you didn't read about it before, the right answer. And the right answer is that for a brief friction of a second, you have nothing, and then one of the image randomly, you can test it by switching the picture, switching the eyes, and so on and so forth, emerging to your consciousness. It's present there for 8 seconds on average, then it disappears, and the other image appears. Then it disappears, and it goes in endlessly until you would do something else with your brain. So this is another demonstration that we see with the brain, not with the eye. Okay, I actually have 7. Actually, I'm only now going to show you the project. So actually, when we bumped into the work of Paul Bacharita, which basically mainly used the touch sense to represent vision. So basically, Paul Bacharita already was thinking about this. That maybe if we see with the brain, not that we see with the eyes, then maybe we can make a bypass and encode information from vision in touch, like in the example I showed you initially, or like we do in Braille. What is Braille reading? We take but only to one category. We take a visual symbol, encode it in a different modality. And then they will be able to see. What we did, we thought it would be really cool if we could, I'm a musician in my background, a failed musician, And I thought it would be really cool to take the visual image and encode this information in music, and actually produce the first color visual sensor substitution, and see how the brain adapts to understanding this type of information. So I won't have too much time to show you all the principles, but even without telling you anything about the algorithm, I can tell you just that there is a pentatonic scale here. If you want to know why pentatonic, you need to listen to Bobby McFerrin's beautiful TED Talk, how universal it is, and it's sweep from left to right, and you are integrating over time on the image. So there is some cross-modal correspondences between vision and audition. So here is the... So without even telling you anything, you feel the correspondences between vision and audition. And we also have a glove that we created that works on the same thing, so you can get touch information, sound information, whatever you prefer, both, which one most prefer. Basically using this, they can learn to recognize grayscale images, but also they can learn to do colors by the fact that different musical instruments are representing different colors. So there is some training, and they learn to interpret also colors. I'm not going to show you all this, but you can see how you can separate your body, which has more reddish colors in the algorithm, from the white, which is the coir, and so on and so forth. And there is some learning process that you are going through it. I would skip all this. I just want to mention what happens to the blind when they start learning this. So we created a whole free web-based, it used to be a lab, now last month we are uploaded all this training into the website. And blind that work with this represent 3 stages, which I think is one of the most amazing setups to study consciousness, which is a very difficult issue to study in the human brain. And what it means to have a new sense or to regain a lost sense, okay? So what is happening with them is, for example, with the glove, but the same is with the ear. The first stage, you just hear or you feel touch on your body, and this is a tactile sensation. It has nothing to do with vision, although it's coupled to a camera. The second part is called discrete attribution. When I start to learn these cross-modal correspondences, I am basically mapping from one sense to the other, and I understand that the information not coming from here, it's coming from there, from a place which I cannot reach with my hand, or I can reach with my hand. And then in some cases, especially of course late blind, that use it a lot, starts to develop a hallucination or a reactivation of their visual images that they stored using the ears they used to see by using a lot of these cross-modal correspondences. And what we ask in this project, what I will do in the last 3 minutes that I have, is show you what happened in the brain when they learn to do it, but we can ask the same thing, can we create a new sense using non-invasive approach just like this by doing this coupling and teaching the brain to go through this process. So one of the projects is using, for example, Wi-Fi signaling and trying to use it for social consequences, for example, in Asperger syndrome individuals to have more awareness to people entering the room and outside and so on and so forth. This is just a little pilot on these new senses. But I'm going to show you a 1-minute movie of a congenitally blind, this is Hamutal, using this setup and learning to, I'm showing you only part of this movie. And she is analyzing cognitively, she's still in this distal attribution period, and understanding what is the facial expression of a la by using these sounds just like a bat, but using this iMusic algorithm. Okay? Or in this case, the voice algorithm. And their generation to a different part. Now, what happens, I will skip this. Now to the brain a little bit. What happened to the brain? I have 2 minutes, so I will summarize very, very briefly. We actually think that all the way that we think about brain organization and brain plasticity are somehow need to be updated or completely revisited using the results that we found here. So for this, I have to teach you 1 minute of anatomy, of a very gross anatomy. The red areas are 2 streams of the visual system, one that analyzes shape, tools, faces, everything, and color, and the other that is used to guide us to act on these objects. And the blue areas are these areas that are used for language, for music, for hearing the dog, and so on and so forth. So, and this is the body representation. Okay, so actually what we found is that, I won't get into this, but there is the notion of cortical plasticity and critical periods I don't have time to say something too much about it, but the Nobel Prize winning work showed that if, for example, you don't get visual input in the first part of your life, you will never develop specializations in the brain. In this case, specialization to which eye you get the information. So these columns represent different eyes in the cortex. So even if you restore the input 100%, you would never get back these specializations. So we ask, what happened to the brain when you learn to see different visual functions? And what happened in the brain in terms of the brain specialization? So in 1 minute, I would show you maybe two slides. One is what happened in the brain when the blind learn to see faces or to read. And this is they do in tens of hours, like 10, 20 hours of learning. And I won't get into the method, but it's a bit heavy on computation. But basically what you see here is that the first signal is the onset of the signal is being sent to the auditory system, which is doing very quick analysis of the heights and the volume. But who is building the topography that this is actually a face or a smiling face or a word is actually the visual system. And when you recognize it, it's the visual system that is working. Although these are people that never experienced vision, they never had their retina developed. And not only this, all their specialization, I would have time to show only one example. For example, we have a very important system, which is the mirror system. This system enables us to learn by imitation, to see and to execute the same motor action. It's very well preserved in evolution. You can see here how this cute cat is doing it. It's actually so well preserved in evolution that even human can do it. And I don't know if you noticed, but I'm a very serious scientist, so I went to all the... And we found one animal that is not obeying this. But this is just a joke. But the main input to this mirror system is a visual structure that specializes in analyzing the bodies of people. Maybe we'll hear both about it from Daniel. But basically, if you don't have all this visual experience and this specialization to body, what happened to you? What happened to your brain? And can you develop this specialization while you learn to analyze? So we actually use this setup to ask it, and we show that you can learn to imitate visual input. This is the initial part of the training. Then we put Hamutal in the scanner and other people that wanted to participate in the study, and found out that actually they show a complete overlap of that specialization that developed not before, but after they learn to categorize and to understand other people's body by vision, which is represented by sounds versus by sounds. And we went over into the entire visual system. So for example, we showed that a specialization for reading develops in braille. It can develop when you are learning to read using sounds, and for faces and so on and so forth. I won't have time to all of this, but basically what we summarize is that the organization, this is the last sentence. I'm jumping through all this heavy brain stuff.
Our lunch is waiting for us. So.
Yeah. So I would finish with just saying that basically, this is the summary slide, going through teaching each one of the specialization that we have in the brain, face, reading, object, and so on. We can retrain the subject to perform this type of categories, and then see a development of specialization, which is driven by the computation and the task, but not by the sensory experience that the people had in their life, or the input that they are giving. Okay? And now we're actually using it to build a multisensory bionic eye, together with our colleague in Paris, in which we'll use the information from the camera to stimulate the nerves, but at the same time give sound and touch information, and the initial pilot sees that they learn much faster to interpret the sounds, just like we interpret the dress or the FedEx differently when we know what is coming to us in a matter of several hours or tens of hours. Okay, thank you so much. Sorry for taking